Hello class, welcome to Geometry Lesson 1-4. It's all about inductive reasoning. By the end of this lesson, you should be able to use inductive reasoning to make conjectures about mathematical relationships. So inductive reasoning means that you can find patterns, okay? Looking at what you have and looking for patterns in order to guess what will come next, okay? So if we look at this first example, and we want to figure out what would appear to be the next two terms in each sequence. Okay, so if I look at letter A, I'm going from 88 to 82. Okay, so just thinking, okay, I went down 6. 82 to 76, I went down 6. 76 to 70, again, I went down 6 or subtracted 6. 70 to 64, I subtracted 6. So it's safe to say that in order to find the next two numbers, I'm going to subtract 6 again. So 64 minus 6 would give me 58, and 58 minus 6 would give me 52. So those would be the next two terms in the sequence. And that train of thought, that finding that pattern and extending it, that is called inductive reasoning, okay? So if we look at letter B, going from 3 to 5, I add 2. From 5 to 9, I add 4. From 9 to 15, I add 6. From 15 to 23, I add 8. So I think it's safe to say that next I would add 10. So that would give me 33. And then I would add 12, which would give me 45. So my next two terms would be 33 and 45. Okay? Why don't you go ahead and try to determine what the next two numbers in this sequence would be? Hopefully the next two numbers you got were 50 and 25. You saw that each number was being cut in half or divided by 2. And so 100 cut in half would be 50, 50 cut in half would be 25. All right, let's look at example 2. Use inductive reasoning to make a conjecture. So conjecture is an unproven statement or rule that is based on inductive reasoning. So something that you presume to be true, but it hasn't been proven yet. Okay? So if we look at this pattern of dots, let's see if we can find what the pattern would be. So if I'm on the first term, I have 2 dots. If I'm on the second term, I have 6 dots. Third term is 12. Fourth dot is 20. So I want to see how are these numbers related. So if I look at the very first term, I have one row, right? Remember, rows go left and right, and then columns go up and down, okay? Just to help you keep track of what I'm saying. So I have one row, and I have 2 columns. In the second term, I have 2 rows and 3 columns. In the third term, I have 3 rows and 4 columns. The fourth row, I have 4 rows and 5 columns. So, interesting. If I compare these, I can say, if I want to find something for the nth term, that could be the 5th term, that could be the 6th term, the 7th term, it could be the 100th term. But I'm not going to specify. I'm going to use n instead. So first, let's maybe look at how would we find the 5th term. Well, if we had the 5th term, you can see we would have 5 rows, right? And then how many columns would we have? How are these numbers changing? They're going up by 1 each time as well. So that would mean 6 columns, right? Okay, so I'd have 5 rows and 6 columns. How could I write this as in terms of n? Well, if you then look at how these numbers are related, 1 times 2 is 2, 2 times 3 is 6, 3 times 4 is 12, 4 times 5 is 20, 5 times 6 would give me 30. So what I'm doing, I'm essentially just multiplying the two numbers. So my equation could be whatever term number, so I could use the nth term, I'm going to multiply by n plus 1. Let's see if this works. So if I'm on the first term, n represents 1, right? So I'd have 1 times 1 plus 1, which is 2. So 1 times 2 would be 2. That works. What if I tried the third term? I'd have 3 times 3 plus 1, or 3 times 4, which is 12. That checks out as well. So if I used this information in order to come up with my pattern, n times n plus 1. Okay, that would be my algebraic expression. Why don't you use this new pattern to determine how many dots are in the sixth term of the pattern? Good luck. Hopefully you ended up at 41 dots for the sixth term. Now, what conjecture can you make about the number of dots in the nth term of the pattern? Hopefully you ended up at n squared plus n minus 1. Okay, that might have been a little tricky to figure out because we haven't done stuff like this since last spring. So if that was tough, don't worry about it. We're going to keep working on stuff like this. You're going to be okay, I promise. But make sure you ask questions. Let's look at example 3. Use inductive reasoning to make a prediction. So use the pattern to predict the number of voters in the 7th election. And we have this nice little table over here that gives us the first year. We had 3,511 residents and 386 voters. And it goes through 1st, 2nd, 3rd, 4th, 5th, 6th, and then we want to figure out the 7th. So in order to figure that out, let's figure out maybe about how many, like what percentage of the voters was this. So if I did 386, ooh, my smartboard's being weird, 386 divided by 3,511, I ended up at, that's about 10.99, that ends up being 0.1099, or about 10.99% of people voted. What about in the 4th year? What if we had 544 of the 4,907? That works out to be 0.1109, or about 11.09%. And then what about, let's do a third one. Let's do the 6th year. So 767 divided by 7,014. That's 0.1090, or about 10.9%. So we're pretty close to the 11% each year, right? So what I'm going to do, I'm going to take that 7,786, and I'm going to multiply by 11%. Remember, percentages we convert to decimals. And that ends up being about 856 voters. Okay. If you have any questions about that at all, please be sure to put a star next to it and ask. But go ahead and try this one on your own. Hopefully for this one, you saw that based on this data, how many members would you expect in the chess club to have in its 5th year? Well, let's look at how the numbers are changing. From the 1st to 2nd year, we added 3. From the 2nd to 3rd year, we added 4. And from the 3rd to 4th year, we added 5. So going to its 5th year, we could assume that we're going to add 6 people. So we should have about 28 members. Now, if you tried to do a percentage between the two, you probably didn't get the same answer. You have to look and try different methods and see what answers make sense, okay? Might take a couple tries of different ways to get to the correct answer. Example 4, find a counterexample. So we want to find something that proves this wrong, okay? So my conjecture is that a polygon with diagonals has 2 fewer diagonals as sides. Now we want to find a counterexample. So I just put a bunch of polygons up here so we can test out some diagonals. So on this 4 sides, we have 2 diagonals. We're looking for a counterexample. So something where that proves that not all polygons with diagonals have 2 fewer diagonals as sides. So the square, not a counterexample because 2 diagonals, 4 sides, that's 2 fewer diagonals than sides. What about a pentagon? Here's a diagonal, 2, then I could do 3, 4. Another one would be right there. So that one is actually 5 sides and 5 diagonals. So a pentagon is considered a counterexample because it has the same number of sides and diagonals, but it's still a polygon. Okay, so what would a counterexample be for the following conjecture? If an animal has 4 legs, it is a dog. Hopefully you were able to rattle off a bunch of animals with 4 legs, but I mean you could do cat, horse, frog, giraffe, hippo, so many options, but you just need to list one to prove that a dog is not the only 4-legged animal. All right, example 5, what about testing a conjecture? So for each conjecture, test the conjecture with several more examples or find a counterexample to disprove the conjecture. So letter A polygon with 4 congruent sides and 4 right angles. So we have a polygon, and it has 4 congruent sides, and it also has 4 right angles. So we want to know what could disprove this, okay? Well, a square would fit this criteria, right? We'd have 4 congruent sides and we'd have 4 right angles. But what about if we had a polygon that had 4 congruent sides, but we don't have the right angles? So a square fits the criteria, but this slanted square or a rhombus does not fit the criteria. So this would be a counterexample to what is stated. It has the first part, but it's missing the second part. Okay? There's no right angles. Now, letter B, if a number is a multiple of 9, then the sum of its digits is also a multiple of 9. So we're looking at 2 things. Multiple of 9 and sum of the digits. Okay, so multiple of 9. We could do 9 times 2 equals 18. That's a multiple of 9. So then I'm going to go over here and add up the digits. So then I have 1 plus 8 is 9. Is 9 a multiple of 9? Yes. Okay, so then I could go over here. I could say 9 times 3. That's 27. 2 plus 7 equals 9. 9 is a multiple of 9. Could do 9 times 8, 72. 7 plus 2 equals 9. Okay? that's 3 different examples of it working. We can say true for this. That is actually a true conjecture. Go ahead and see if you can test this conjecture with several more examples, or find a counterexample to disprove this conjecture. And I'll help you a little bit. I'll say that you're going to want to look at numbers that are divisible by 4, and then sum of last 2 digits. So whatever number you divide by 4, the sum of the last 2 digits should be divisible by 4. All right, so your tests might have been different numbers than what I just included here, but here are 3 examples of it working. So I can safely say that this is a true conjecture. If you have any questions about this problem or anything from the lesson, please be sure to reach out to myself or a friend for some help. Have a great day.